Hello. So in this video we're going to be talking about absolute values and in particular the geometric understanding of these things. I'm also going to fold in a little bit about sort of standard notation and that kind of thing, but we'll cover a lot more of that in greater detail when we talk about the analytic view. So just as a sort of quick reminder, just so we're all on the same page, when we talk about absolute value, we're talking about exactly the thing you were thinking about. So for example, we would have some f of x equals absolute value bar x, this kind of function, right? But it turns out that as sort of unpleasant as this function is analytically, and we'll get there, geometrically, it actually is a pretty natural thing to talk about. So notation, right, the absolute value bars, I'll also make just a quick comment in case, depending on the sort of text you use moving forward, you sometimes see this with a double bar. So you might see it as something like this. So this is technically a different math thing called a norm, but unless you take an upper division math course, you'll never have to worry about that. So until you get to the point where they talk about this symbol in particular, you can sort of equate these two symbols at a sort of pre-calc level and a calc 1, calc 2 kind of level. So if you see a double bar, it's essentially the same as a single bar, unless you're sort of far enough along in math where at that point you'll know the difference. So that's the notation bit. In terms of the sort of understanding though, there's sort of two main pieces to this. One is that we understand the absolute value. So absolute value is this thing that makes numbers or things positive. So you may have learned this back in algebra or whatever. This is a little sort of opaque though. It doesn't really lend a lot of insight as to what an absolute value is or what it does. So the sort of better version for geometric understanding is that it can represent, so one of the sort of key or common aspects or things that we use for modeling is distance, specifically distance between values. So in particular, if you want to say, the distance between x and 5 is 7, well, so in fact, let me do sort of a concrete example here. Let me maybe make a nicer version than what I just said. So distance between, let's do x and 3 is 2. So let's sort of look at what this means. So what this means is, if we think of like a number line, right? We'd have 0 over here somewhere. So we could do some like 2, 4, 6. So we have the distance between x and 3 is 2. So x is the thing we don't know, right? Its distance from 3 is 2. So that means I'm starting at this 3 value here, right? And then I can go up to 2, use a different color because that's a little hard to see the difference. I can go up to 2 units away, and that's where x is, or I should say in particular it is exactly 2 units away. So I could go 1, 2 over here. So this is a possibility, right, at 5. Or I could go 1, 2 over here, and that at 1 would also work. And if we think about what that means, right, from a distance standpoint, right, the distance from 3, well, 5 is 1, 2 units away, and the distance from 3 for the number 1 is 2 units, right, 1, 2 units away. So x could be either one of those and it would work. But how will we write a function or some relation that represents this? That's the question. So that's where the absolute value comes in. So when we look at the distance between two things, we're going to put those in absolute value with a subtraction, meaning if we take the difference of x and 3, we should get 2. Now you may wonder why subtraction, but if you think about it, if you want to know the distance between 5 and 3, what do? Well, you would take one of them and subtract the other, right? 5 minus 3, that distance would be 2. And you could do the same thing with 3 and 1. Now you might run into a little bit of a problem depending on which way you do it, right? If you know the numbers beforehand, 3 minus 1, that's 2. But if you did 1 minus 3, well, that would be negative 2. And we still want to have 1 as an answer, but the distance shouldn't be negative 2, right? We want distances to be positive values. So that's where this absolute value is coming in. It's saying, okay, take the point you think works, like 1, subtract 3 from it. So 1 minus 3 is negative 2. Look at the positive version, right, the distance idea, and you should have 2. And that's exactly what we get here. Okay? So sort of a common model for absolute value, you want to think of it as distance. Now if we look at just absolute value of x, it's not quite in this form, right? So distance, in fact, well, yeah, let me put it over here. So if I say distance between, and then let me actually do different colors here. So let's do x and some other number, which I'm going to write as a, where, right, a was 3 over here. So the distance between x and a is written as the absolute value of x minus musical pens over here, a, close. So again, the same idea, right? We had x minus the point 3 here is now this sort of general a thing, right? But, so if I do this for distance, the question might be, or a question might be, what does just absolute value of x mean in this context, right? Because the claim here is that this is sort of a good way of understanding what an absolute value is. And here the trick is to rewrite this absolute value of x, we can actually rewrite as, I'm going to try to be consistent here, x minus, oops, I say I'm going to be consistent and then I immediately fail. Let's try that one again, huh? X minus, so I want to have x minus something, but it needs to just be x, meaning I have to subtract something without actually subtracting something. So that has to be what? Has to be 0, right? 0 is the only thing I can subtract from x without actually changing it. So this is really 0, meaning that absolute value of x is really the distance between x and 0. So if we have just the absolute value of something, what we're really asking is what's the distance between that thing and 0, right? And I'm pointing this out because that definition, which you may have heard before, the distance from 0, is not sort of incompatible with this other idea. They're the same idea, I've just sort of generalized it instead of being only from 0, being from between 2 different things. This is a very common thing to use, even in upper level math, actually, so it shows up a lot because it's a very sort of handy way of representing this, okay? So again, this sort of geometric view, this geometric understanding, you can think of it as sort of distances between things. The last thing I want to mention or cover here is how one would graph these things, right? Because again, geometric view, one of the common geometric views we use is graphing. And the sort of most common context to do would be some sort of inequality. So for example, if I want to graph, I'll do it here. So graph, let's say the distance between x and 3 is, let's say, at most 5, okay? So at most means it is that or less than that. So what that's going to mean then is I'm going to go less than or equal, because it can be that thing or less than that thing. I said less than or equal, so at most 5. In the actual Chronos text, I go through common sort of words you see: at most, at least, less than, greater than, etc., and what they sort of associate as symbols. The general rule of thumb is it sort of should be an intuitive process, right? Ask yourself, can it be that thing and still work? If I say, you know, the distance is less than 5, is 5 less than 5? No, then it shouldn't be less than or equal, it's strictly less than. This is sort of general idea. So if I'm graphing this, again, the idea here is that I'm going to have my number line, right? I'm going as a distance from 3, so let's say I have 0 here. So 2, 4, 6, 8. So my distance is starting at 3. The distance is at most 5 away, meaning I can go at most 5 in each direction. We can talk about, and we will talk about in the analytic view, how to do this sort of with actual algebra analytically. But until we get that far, I will just say, okay, I can go up to 5 units right and left. So if I go 1, 2, 3, 4, 5, 8 is going to be one side of it, and I can include 8, right? And then if I go the other way, I'm going to have 1, 2, 3, 4, 5, -2 will be the other side, and I can include it, so I'm using a square bracket. And I can have anything in between, because the distance can be 5, but it can be less than 5. So I could have, for example, x equals 3 would make sense because the distance between 3 and 3 is 0, which is less than 5. So all of this then would be the solution. It's sort of commonplace to write out the solution sort of pieces to get the solution above and below, and we'll see more of this as we go forward. But you can, you want to eventually write the real solution either on the number line or make it clear what is your solution. So this is the only thing I graphed, so this is fairly clear that it is my solution. But if I want, I can write my final solution sort of underneath. The key here, though, is that I am coloring in the section, right? I'm including all of this as solution, not just the endpoints because of the inequality. If this were equal 5, then just like it was over here, I would have just the points, because is an equal, right? So this is x minus 3 equals 2, and so I have just these, not the other pieces, because this is not an inequality, okay? So that's pretty much that, geometric view. Distance, great way of understanding it. This idea of making numbers positive is a more sort of analytic way of doing it, and that's what we'll cover next. And this idea of graphing by sort of shading in to represent all the correct values. And we'll see a lot of that later on when we talk about sort of solutions to equations involving absolute values. Okay, so that is that.